Hi everyone, thank you for being here. I'm very excited today to share with you my research in soft composite materials and how it can enable the development of next generation of materials. So let me start by explaining what soft composite materials are through an example and why are they interesting to study. So consider a car tire, as seen here in the top left. A car tire is primarily made out of natural rubber, which is soft and has a milky white color. The tire itself is black in color, which is because if you zoom in on a tire with a microscope, you'll see that the natural rubber is actually embedded with carbon black particles. This is an example of a soft composite material made from a combination of two materials with complementary properties. And such materials are present everywhere, from aircrafts and buildings to the shoes you're wearing to even the biological tissues in our body are examples of such materials. Now, why are they interesting to study? Well, primarily because they're soft and they can sustain large deformations. They exhibit more complex, more rich behavior than hard materials like metals, which are relatively well understood. This is what excited me the most when I decided to work in this area. Furthermore, there's a huge potential to develop new materials with better properties than anything available naturally by combining two or more materials, existing materials together, like we do with natural rubber and carbon black. But the problem with that is because these materials exhibit such complex behavior, conducting experiments to detail their behavior accurately is often not feasible. So this is where I come in. In my research, I'm developing mathematical theories to accurately predict the mechanical behavior of these materials. Specifically, I'm working on a theory to predict how these materials fracture, how these materials break. So I'll give you a very simple example of fracture in soft materials. Think of a balloon. If you pump enough air into a balloon, at some point it won't be able to sustain the pressure and it will break. This simple behavior of fracture under high pressure is seen in a variety of soft materials. You might have heard of aneurysms, which occur in blood vessels. This is essentially ballooning out of the walls of the blood vessels in certain areas, and this can even be life-threatening. Here I've included a picture of the root of a corn plant. These cavities that you see here are also a result of fracture under high pressure. Going back to the example of a car tire, what we see in that case is that fracture initiates in the vicinity of the embedded particles, again, because the pressure in that region is often very high. Furthermore, what we see is that these cracks that nucleate in the vicinity of the embedded particles often heal themselves autonomously. So I have been developing a theory to predict the onset of cavity formation or crack formation and the occasional healing in these materials. To verify my theory, I have been collaborating with another research group who have done experiments on specimens like that on the lower right with two embedded particles in natural rubber. So far, the comparisons between experiments and theory have been really good, and we hope to do more comparisons soon. The next step in my research is to apply this theory as a design tool for the development of new materials, and that's really the ultimate goal of my research. Thank you.